Hello students, today I am taking some problems based on Euclid division level. One of the problems is that show that square of any positive integer is of the form 3m or 3m plus 1. So how can we solve it? Let a be a positive integer. Since each positive integer is of the form 3q plus 1 or 3q plus 2. In previous question, we have already solved each positive integer is of the form 3q plus 1 or 3q plus 2. So take a equal to 3q plus 1, a equal to 3q plus 2. Squaring. Because we want to show that square of any positive integer. So a square equal to 3q square, a square equal to 3q plus 1 square, a square equal to 3q plus 2 square. This can be expanded. A square equal to 9q square, a square equal to 9q square, 6q plus 1 using the identity a plus b whole square. A square equal to 9q square plus 12q plus 4. In next step, this can be expressed as a square equal to 3 into 3q square, a square equal to 3q square plus 2q plus 1, a square equal to 3q square plus 4q plus 1 plus 1. Because 9q square plus 12q plus 4 can be expanded 9q square plus 12q plus 4 as 9q square plus 12q plus 3 plus 1. So next step, this can be written as. Now, this can be expressed as a square equal to 3m, a square equal to 3m plus 1, a square equal to 3m plus 1. M is some integer. In this format, q is some integer. Q is some integer. And we know that well, a square of integer again an integer, sum of two integers again an integer. So a square of any positive integer is of the form 3m or 3m plus 1. So this is one problem. Here we want to show that a square of any positive integer is of the form 3m or 3m plus 1. So we will take here any positive integer a, and we know that well in previous question we also proved that each positive integer can be expressed in the form of 3q plus 1 or 3q plus 2, where q is some integer. So a equal to taken a equal to 3q, a equal to 3q plus 1, a equal to 3q plus 2. But in this problem, we want to get square of any positive integer, is of the form. So we take square in each term. a square equal to 3q whole square, a square equal to 3q plus 1 whole square, a square equal to 3q plus 2 whole square. After expressed using the identities, a square equal to 9q square, here use the identity a plus b whole square, a square plus 2ab plus b square. So a square equal to 9q square plus 6q plus 1. Similarly, this also can be explained. Now next step, this can be written as a square equal to 3 into 3q square. A square equal to, take common from these two terms, 3q square plus 2q, 1 is outside, again 9q square plus 12q plus 4 can be expressed 9q square plus 12q plus 3 plus 1. So take 3 common from first 3 terms. So a square equal to 3, 3q square, 4q plus 1. These assume as integer, again integer, again integer. So a square equal to 3m, 3m plus 1, 3m plus 1. So these two terms are repeating. So we can say that square of any positive integer is of the form 3m or 3m plus 1. Thank you. Hello students, good morning. Now we are starting a new topic based on real numbers, is fundamental theorem of arithmetic. What is the concept of this theorem? The theorem statement says that every composite number can be expressed as the product of its primes, and then expression is unique, and this expression is unique. What is the sense of this statement? So we discuss about the composite number and primes, prime numbers and composite number. So what is the sense of prime number? All those numbers, they cannot be split into the product of two primes. For example, 2, 3, 5, 7, etc., in which each number cannot be expressed as the product of its prime. 2 cannot be split, 3 cannot be split, 5 cannot be split. So these type of numbers are called prime numbers. Composite number. The composite number are the numbers, they can be split two or more than 2 primes. For example, 4. So 4 can be expressed 2 into 2. 6 can be expressed 2 into 3. Both are the primes. 8 can be expressed 2 into 2 into 2. So these type of numbers, they can be split 2 or more than 2 primes are called composite numbers. The statement says that every composite number can be expressed as the product of its prime, and this expression is unique. So what is the sense of this statement? For example, 12 can be expressed 2 into 2 into 2. So in the factorization of 12, we are using 2, 2 and 3. So this expression is unique, because how we can number of factorization of 12 any times, but we get only 3 primes, 2, 2, 3, or 2, 3, 2, or 3, 2, 2. So these 3 primes are already available in the factorization of 12. Similarly, suppose if I am taking 15, so 15 can be expressed 3 into 5 or 5 into 3. So this is the sense of this. Expression is unique. This means in the factorization of any number, always the fixed numbers are repeat. So this is the statement of fundamental theorem of arithmetic. Now I am taking some problems based on the fundamental theorem of arithmetic. Thank you. Now I am taking some problems based on fundamental theorem of arithmetic. In these problems, we discuss about the factorization of a composite number. The problems are in the way express the following as a product of prime factorization. These three numbers are given. The first part of this question is that 140, in second part 156, and third part 700. So we start with first part, A, 140. So 140 can be split in its prime. 2 7 ja 40, 140, again 2 35 ja 70, 5 7 ja 35, and 7 1 ja 7. So these factors can be expressed as 140 equal to 2 into 2 into 5 into 7. These prime factorization also can be expressed as factor tree form. So here start with 140. This is the first prime factor. 72 is 140. Again 2 is prime, so fix there. Now 70 again reduce. 35 2 is prime. This is fixed. Again 35 can be reduced as a 70. 75 to 35. These both the numbers are prime. So process is finished now. So our prime factors are there 2, 2, 5, 7. Just like that. In second problem 156. So 156 can be split 2 7 ja 14, 2 8 ja 16. In next step 2 3 ja 6, 2 9 ja 18, 3 13 ja 39, 13 1 ja 30. So 156 can be expressed 2 into 2 into 3 into 30. And as in the form of factor tree, 156 reduced in 78 to ja 156. 2 is fixed here. Now again 78 can be expressed 39 to ja 2 is fixed. Now 39 again expressed 33 ja 39. So these both are the primes. So our process is finished now here. So last the total prime factors are there 2 into 2 into 3 into 30. So this is a prime factorization of 156. Now we take the last part of this question. C part is there 700. So by prime factorization 2 3 ja 6, 2 5 ja 2 0 ja. Again 5 7 ja 0 ja. Again 5 14 ja. Again 2 7 ja. Again 7 1 ja 7. So 700 can be written as 2 into 2 into 5 into 5 into 7. By factor tree 700 can be reduced 350 and 2. 350 again reduced 175 into 2. 175 again reduced 5 3 ja 15, 5 5 ja 75. 35 again reduced in two format 7 5. So both are the primes. So our process is finished now. So the final prime factors are 2 into 2 into 5 into 5 into 7. This is the prime factorization of these two numbers. Okay. Hello students. Now I am taking a new topic based on real numbers, SCF and LCM by prime factorization. If A and B are two given numbers, then we want to find LCM and SCF of A and B. Then first we find prime factorization of these numbers. Suppose that we want to find the prime, we want to find the SCF and LCM of given two numbers. Then first our process is that, algorithm is that we find prime factorization of given two numbers A and B separately. After it, the formula is that SCF of given numbers A and B is product of smallest power of each common prime factors in given numbers. First, and LCM of AB, product of greatest power of each prime factors involved in numbers. So, for understanding these identities, we have made some examples. Find LCM and SCF of 92 and 510 using prime factorization method. So first we take prime factorization of 92 by this process. 246 is 92, 223 is 46, 23 1. So the prime factorization of 92 expressed as 2 into 2 into 23. Similarly, 510 can be reduced. 2 2s are 4, 2 5s are 10, 2 5s are 10, again 3 times, again 5 times, and again 17 times. So prime factorization of 510 can be expressed 2 into 3 into 5 into 17. So first we write both the prime factorization of given numbers. Now SCF of 92 and 510. The formula is saying that product of smallest power of each common prime factor. So observing here, only 2 is common in both the prime factorization of given numbers. So SCF of 92 and 510 is given by 2 the power 1 because the single power of 2 is common in both the numbers. So SCF of 92 and 510 is expressed by 2. LCM of 92 and 510, product of greatest power of each prime factors. So take here, so first we choose least prime 2. So here 2 has the power 2 and in this factorization 2 has the power 1. So greatest power is 2, so we take 2 the power 2. In both the prime factorization, next prime is 3. In this factorization 3 is absent, but greatest power of 3 is present here 1, so we take 3 to the power 1. Next prime is 5. So in both the factorization, 5 have the greatest power 1, so we take 5 to the power 1. In both the prime factorization, 17 has the greatest power 1, so we take here 17, and similarly 23. So product of these numbers is given by 2, 3, 4, 6, 0. So the SCF of these numbers is 2 and LCM of these numbers is 2, 3, 4, 6, 0. Now I am taking another problems based on LCM and SCF. The question is that find SCF and LCM of 54 and 336 by prime factorization. So what is the method? First we find prime factorization of these numbers 54 and 336. So 54 can be reduced to 27 ja, 3 9 ja, 3 3 ja, 3 1 ja. And next 336 can be reduced 2 1 ja 2, 2 6 ja 12, 2 8 ja 16, 2 8 ja 16, 2 4 ja 8, 2 4 ja 8, 2 2 ja 4, 2 21 ja, 3 7 ja, and 7 ja. So now 54 can be written as 2 into 3 into 3 into 3, and 336 can be expressed 2 into 2 into 2 into 2 into 3 into 7. So these are the prime factorization of 54 and 336. Now SCF of 54 and 336 is expressed as product of lowest common prime factor. So 2 is common here and here with least power 1. So to the power 1 is there. 3 is common in both the numbers with least power 1. So 3 is there and no other numbers, no other prime factors is common in both. So the SCF is given by 6. Again, LCM of 54, 336 is written as the highest power of least prime. Highest power of least prime in both the factorization is to the power 4. So we take here to the power 4. 2 is present there with single power, but 2 is present there with 4 power. So we take highest power of first prime to the power 4. Next, 3. 3 has a single power here, but there is the highest power of 3 is 3. So we take 3 to the power 3. And next, and there is present there 7 with single power 1. So 16, 27 into 7. 16 into 7, 7 is 49, 7 is 14, 189. Again multiply 16 9 is 144, 16 8 is 128, 138, 142, 16 1 is 16, 26, 30, 3024. So 3024 is the LCM of these two numbers. So what is the process? I am repeating again. First we find SCF and LCM of 54 and 336 by prime factorization. The first step of the process is that we find prime factorization of both the numbers 54 and 336. These are expressed as 54 can be expressed 2, 3, 3 and 3, and 336 expressed as 2, 2, 2, 2, 3 and 7. Now SCF of 54 and 336 written as the smallest power of the prime common prime factors. So 2 is common there with single power and 3 also common there with single power. So 2, 3 is 6. And in the LCM we take the highest power of each prime factor present in number. So 2 is present there with highest power 4, 3 is present there with highest power 3 and 7 present there. So this is the LCM of these numbers. Now one more formula is given here. SCF into LCM. SCF of AB multiplied by LCM of AB is equal to A into B. This formula is valid for only two numbers. Some questions can be asked by you. Find the SCF and LCM and verify this equation. SCF of given number, LCM of given number is equal to the product of these numbers. So we take some problems based on this type of formula in next topic. Hello students, today we are discussing the topic SCF and LCM by prime factorization, some problem based on this topic. The problem is there, find LCM and SCF of 100 and 190 by prime factorization and verify that SCF into LCM equal to product of numbers. So how can we solve this type of problems? So first we find prime factorization of 100 and 190 separately. So 100 can be reduced, 250 are, 225 are, 55 are and 5 ones are. Similarly the prime factors are 2, 2, 5, 5. Similarly 190 can be reduced, 295 are, 590 are and 91 are. So 190 can be reduced to 519. Now we come on SCF. SCF of 100 and 190 can be written as the minimum or lowest power of common prime factor. So 2 is the common factor is there and lowest power is 1. Similarly, 5 is the common factor and least power is 5, so SCF becomes 10. And now LCM of 100 and 190, we take highest power of each prime factor. So first prime factor is 2. Here the highest power of 2 is 2 and minimum power is 1, so we take highest power to the power 2. Second prime factor is 5. Here the highest power is 2 and lowest power is 1, so we take highest power 5 to the power 2. Similarly, highest power of 19 is 1. So this can be expressed 4 into 25 into 9, 1900. So LCM of these numbers is 1900, SCF is 10. Now we verify this equation, SCF into LCM. So SCF into LCM is, both the numbers is 10 and 1900. This is 19,000. Similarly, product of these numbers 100 and 190, right here 19,000. So this is a verification of SCF and LCM of product of is equal to the product of numbers. Now we take one more problems based on this formula. So we change the digit now here, okay, and take find the SCF and LCM of 105 and 120. 105 and 120, and again verify that SCF and LCF of product of is equal to the product of numbers. Now how can we solve this? 105. First we find prime factorization of 105. So here take 105. 3 3 is 9, 3 5 is 15. Again 5 7 is 35 and 7 is 7. So 105 can be reduced 3 into 5 into 7. Similarly, 120 can be reduced 260 is 230 is 215 is 3 5 is and 5 1 is. This is the prime factorization of 120. So 120 can be expressed as 2 into 2 into 2 into 3 into 5. Now SCF of numbers are 105, 120. This can be expressed. So 105 and 120. So first common factor is 3 in both the sides. With least power 1, so 3 to the power 1. Similarly, next common prime factor is 5. So we take least power of 5 is 1. So the SCF is 15. And LCM, what is the process to find the LCM? Are you aware? Take highest power of each factor. So first factor is 2. So to the power 3 with highest power, 3 with highest power 1, 5 with highest power 1 and 7 with highest power 1. So 2 power 3 become 8, 3, 5, 7, that means 8 3 is 24, 24 5 is 120. 120 into 7, so 7 0, 7 2 is 14. 840. This is the LCM. Now, the next part of the question is SCF into LCM of these numbers is 15 into 840. This is equal to 15 0 is 50, 0, 15 4 is 60, 15 8 is 120, 128, 12,800. Product of numbers is equal to 105 into 120. So take product 120 into 105, 0, 5 to the 10, 6, 0,